All right, we receive your video whenever you're ready.
You can see it? Okay, great.
Yep.
Okay. Okay. Hello, and my name is Ekta Sood. I'm going to be presenting the paper Multimodal Integration of Human-like Attention and Visual Question Answering. And thank you for your time. Okay, so I would like to start with visual question answering as just a general kind of introduction. VQA is an inherently multimodal task where we have an image and a corresponding text, and the system is required to answer the question. So in this case, you have an image of a person with a banana mustache and the question, what is the mustache made out of? And we require the system to answer with the ground truth annotation bananas. Subsequently, we've seen that by incorporating neural attention mechanisms into various downstream tasks, including visual question answering, we observe improved performance. So essentially by, can you still hear me? Okay. Yep. Essentially by incorporating the sort of cognitively inspired visual saliency algorithms, we can help the model focus on relevant parts of the input modalities. In order to further enhance performance in tasks like visual question answering, some research has used human attention or human-like attention as a supervisory signal to further refine the model's ability to focus on relevant regions of the image or corresponding image. But such integration strategies have been largely limited in that they were only integrating human attention or human-like attention from the image. So they were limited in only integrating a unimodal attention signal. So what we do here is we try to integrate human attention on both the text and the image instead of just the image. And this limitation was largely due to the fact that there just was not a saliency prediction model or some kind of attention prediction model for text. So that's a little bit of a plug from previous work of ours where we produced the text saliency model, which we showed and validated was able to produce human attention over a variety of different types of text. So we leveraged that in this work. And ultimately, we proposed the solution for multimodal integration via the MULAN network or multimodal human-like attention network. In order to integrate multimodal human-like attention into VQA models, we leverage two state-of-the-art human saliency prediction models for both the input modalities, both the text and the images. And on like a high level, this is what it looks like. You have some text, you have the image. We feed that to a state-of-the-art visual question answering model. In this case, it was the MCAN network, which is a transformer-based model. We also feed the individual text and images to the corresponding modality-specific saliency prediction models. And then we use the outputs of these models and integrate them into the neural attention layers of the MCAN network. So our main contributions here is that we provide the first method to jointly integrate multimodal human-like attention on text and images into visual question answering. We achieve competitive performance compared to state-of-the-art on the VQA V2 benchmark dataset, while requiring around 80% fewer trainable parameters compared to current state-of-the-art approaches. So by leveraging the saliency prediction models, leveraging the output from these saliency prediction models and integrating them into the neural attention layer of the VQA model, we can actually obtain competitive performance while maintaining computational efficiency. In addition, we provide insights by performing analysis across different error cases and challenging questions in the VQA V2 dataset. Here's an overall architecture. This is the architecture of our approach. Notably, I want to point out the two additions to the baseline MCAN network, which is the TSM, the text saliency model on the top here, and the image saliency model on the bottom here. And then we integrate those predictions into the self-attention module of the MCAN network for the text and image streams respectively. And essentially here we're taking the output of the saliency model and we're integrating them via dot product in the self-attention module. Here's just a general breakdown using the standard evaluation. So this is just really the mean accuracy. This is the evaluation method that the benchmark data set provides. We wanted to see how MULON improves over not only the baseline of no integration, but also when we integrate human-like attention from only the text, from the textual side and only from the image side. And what we can see here is that by integrating both image and text predictions into the MCAN network, we obtain best performance on the test standard and test dev. We further explore this by looking at category-specific performance. So these categories were proposed in previous work that looked into error cases of VQA models. It's 12 different categories like reading, activity recognition, counting, etc. And what we can see here on the right in bold is that for 8 of these 12 different categories, MULON outperforms the other variations. So both unimodal integration only and also the vanilla MCAN with no integration. Here's some visualizations as well. This is essentially just to showcase that what we observed is, particularly in cases where you have many different objects within an image or very long sequence lengths, that the integration strategy, it helps the model to focus on the relevant parts of the image and text. So for example, when you look at the last epoch here, 13 for no integration versus integration, you can see in no integration, the attention is rather scattered across this all across the image because the image has a lot of different elements in it. And when you look at the MULON network, the attention is rather refined and focused into the relevant part, which is where the child is digging around and and subsequently we get the correct answer with the MULON network, which is a refrigerator. Okay, so just to conclude there, we propose MULON. This is the first method for multimodal integration. We achieve competitive performance and we maintain computational efficiency. But I think the most important takeaway is that we just sort of scratch the surface and provide the evidence for the potential of integrating human-like attention on both the image and text as a supervisory signal for visual question answering and other visually grounded language modeling tasks. Okay, thank you. That's my talk and happy to take any questions.
Thank you, Ekta. Do we have any questions from the audience, including those online? We'll take questions just for this presentation as Ekta is presenting remotely. Okay, I have just a quick question, Ekta. Just curious about the performance differences. Should you swap out the MCAN model with any other model?
Yeah, so we tried and we're kind of working on that right now, exploring different models for integration. At the time that we chose this, it was just a choice because it was the current state of the art at that time. Subsequently, we've tried integration into actually like smaller models that don't use a transformer at all. It's just Luong attention. And we see improvements, but it's not as significant or as much as with the MCAN. Yeah.
All right. Thank you for the answer. Any other questions in the meanwhile that we'll have come up with? All right. Thank you very much, Ekta. Let's thank the speaker again and we'll move on to the next.
Thank you.
Could we have Shu Jin come to the front, please? All right. Just 1 second. I need to start the Zoom sharing.
So hello everyone, I'm Shiwei, and today I will present our work titled Kappa angle regression with ocular controlling awareness for gaze estimation. Okay, first. So let me begin by introducing some gaze-related terminologies in the eyeball as depicted in the right figure. So sorry about there's a typo. Let me open the point. Yeah, so sorry about this. So the visual axis and optical axis should be swapped. So okay, so the visual axis actually is known as the gaze direction, representing the line connecting the fovea and the nodal point and the nodal point end. So the optical axis is on the other hand connects the center of the eyeball and also the pupil center, and it is associated with the observed iris. So the Kappa angle refers to the angle between the visual axis and optical axis, which is an anatomic structure that remains constant within an individual's eyeball but varies across different subjects. So typically the role of the eyeball is assumed to be determined by the role of the head. However, the eyeball actually can roll independently due to the oblique muscles. So there is a human eyeball response called ocular conrolling. When the head tilts to one side, the eyeball responds by rotating in the opposite direction by counter this motion, so which we refer to as the OCR. So here's the video. We can observe that the iris patterns as evidence of the eyeball's effort to maintain a horizontal position when this subject is trying to tilt his head to the side. So now let me present the overall pipeline when we're considering OCR. So when the head tilts with an angle alpha, the eyeball rotates in the opposite direction with an angle of negative beta. So during the image normalization step, the head is brought back to an upright position with an angle of negative alpha. The eyeball rotates accordingly due to this global transformation. However, the role induced by OCR still exists. So this OCR induced a role leads to difference in fovea locations and consequently different directions for the visual axis, even though they are from the same subject's same eye. So it's important to know that this undesired role caused by OCR doesn't alter the angular value of the Kappa angle. It only affects the pitch and yaw components of the Kappa angle. So in other words, if the directional vector is represented by the pitch and yaw, the gaze difference between two images of the same eye cannot maintain constant. Hence, we need to update the formula to incorporate the OCR. So the underlying kappa here means denotes the kappa angle with invariant pitch and yaw. Here, the transformation T function here represents the transformation from pitch and yaw to 3D direction, and the ROCR represents the rotation induced by OCR. So next, we need to estimate the direction of the optic axis to determine the final gaze direction. So we employ STD, a method that generates synthetic images with assigned gaze directions. So in this figure, the left three columns depict the real eye images, while the right three columns display the generated eye images from STD. We assume that the assigned gaze directions as approximate labels for the optical axis direction. So the reason we can make this such kind of like assumption based on the evaluation results using synthetic data, which show a gaze estimation error of around like 2.3 degrees across different subjects. So this error is significantly lower than that observed in real cases during cross-subject gaze estimation tasks. So one reason for this improvement is that the reduced person-dependent variation in synthetic images. So therefore, we propose the following pipeline. So during the training stage, we generate synthetic images to supervise the learning of the optic axis direction, thereby minimizing the person-dependent variation. Simultaneously, we use real images to train the Kappa angle compensation net for estimating the optic axis direction. So we will iteratively update the underlying kappa based on the ground truth and also the estimated optic axis direction. So during the test stage, we will first estimate the subject-specific underlying kappa using the calibration set based on the gaze labels. And then we can use the trained Kappa angle compensation net to estimate the optic axis direction. And finally, we can predict the final gaze direction by considering the regressed Kappa angle, accounting for OCR and the estimated optic axis direction. So moving on to the results section. So we first conducted a comparison between methods with and without using calibration set. So our proposed method achieves better performance than a state-of-the-art methods, particularly the standard deviation here. So you can see we actually compare with the previous method, we can achieve comparable mean performance, but the standard deviation is much better compared with the previous method. So we also evaluated the impact of the number of samples in calibration cells. So our proposed method actually exhibits better performance compared to the difference neural network. It's denoted as DIFFNM. So although the differential neural network reaches saturation performance when the number of calibrated samples exists 32, but our method can still be further improved, especially like if we can have like 64 samples or 128 calibrated samples. So additionally, we present the estimated cup angle distribution for different numbers of calibrated samples. So the right figure shows illustrates the angle error in relation to the distance between the estimated cup angle and the center of the cup angle distributions. So lastly, we provide a comparison of algorithm complexity between our proposed method and the differential neural network. So yeah, thank you for listening. Do you have any questions?
Thank you. I think we have time for a question.
Yeah, sure.
How the resolution matters to, I think you require the very highly resolution images to estimate the cup angle.
So actually, the eye images is restricted around like 64 times 36. So it's not a very high resolution. So the OCR response actually is estimated from the head row before normalization step. So yeah, so maybe in the future, if we can get like very high resolution images, we can estimate the OCR response from the iris patterns instead of like estimate from the row of the head. Yeah, thank you. Yes, please.
So for the OCR effect, is it really a one-to-one correspondence of the head roll versus the eye roll?
So
I think I saw a video that is like zoomed into the eye region,
Uh-huh.
and it's like kind of the eye will be trembling a little bit. So I'm wondering if it's really the one-to-one.
So that's a good question. So basically, the OCR can be further divided into static OCR and dynamic OCR. So static OCR actually is kind of like a one-to-one mapping, and it's very linear, linear relationship between the head row and also the row of the eyeball. So actually, we reference the paper in our workshop paper. So you can check it. So actually, there's another response called the dynamic OCR. Actually, our network cannot cancel that kind of situation because the dynamic OCR is kind of like a fluctuating when the head is rotated, right? So in our case, we just assume all the images are collected under the static OCR. Yeah, thank you. Yeah, thank you.
Thank you very much. Let's thank the speaker again. One moment, please. Next presentation we have on pre-recorded video.
Hello, everyone.
Sorry. All right.
Hello, everyone. I'm Humphrey Wang from University of Birmingham. Today, I will talk about our workshop work, which is named Gaze Caps. It's a gaze estimation method with self-tension rotated captures. People tend to infer gaze by considering different facial properties like gender, race, emotion, which formulate facial contextual information. But few existing methods consider this. Another thing is that certain-based methods are hard to capture facial contextual information because of pooling and straight convolution operators. A large computation load is caused by the self-tension operations of transformers used to grasp the entire context between pixels to images. Our method has three parts. We first input the face images into visual representation part. We use a ResNet 18 to extract the feature from images. And then we reshape the feature into primary capture tokens. At the second stage, we input these captures into SAR module. SAR module is a multi-head self-tension routing. Basically, we use transformers here to explore the information of these captures. And then we use a scratch operation to do activation. After this, we get secondary capture tokens, and then we use SAR module, another SAR module, to regress the gaze direction directly. And finally, we use the ground truth gaze direction to construct a gaze loss for training. And in our method, we replace the dynamic routing in capture light with the self-attention routing to improve performance and also avoid computationally expressive iterations. As you can see in these two images, and for dynamic routing, it requires iterations to update the weight C. But for our self-attention routing, we use transformers simply to explore the relation among these captures and get the weight in one shot. It's quite convenient. For experiment, we compare our method with sort methods. First, gaze captures outputs sort methods on gaze estimation error, as we can see in the first table. And our proposed method has fewer parameters than most existing gaze estimation models, and the lowest flops are among all selected models, as we can see in the second table. We also did cross-based evaluation. The results of scene-based and capture-based methods are put side by side in the table. Our gaze captures shows better generalization performance in all cases. And this result shows that the features extracted from the proposed capture-based model are more robust since it takes the relations among different properties into consideration. And we also did an ablation study on backbone and self-attention routing. Both of capture models outperform scalar models on all selected data sets. The proposed model also shows a better performance than the default capture light with dynamic routing. The proposed method captures average more accurately and have a better performance in gaze estimation, as we can see in this image. Thank you. This is our work.
Thank you very much for your attention. I think we're moving right on to the next presentation, which will be given by Nora. Just a second.
Okay. Hello everyone. I'm Nora Horani. I came from University of Birmingham, and today I'm going to present my work on joint attention target estimation. For the benefit of those who are not very familiar with joint attention target estimation, the task of this research field is to estimate the attention target of 2 or more people within the scene. This is slightly different from gaze direction estimation, when we are only interested in which direction someone is looking at. In this field, we are particularly interested in the target of the attention. So in this field, the methods proposed by different authors and research group can be used for visual navigation and to evaluate the intention and the interest of a group of people together. The existing methods of that exist in this field only rely on 2D data. This made those methods prone to errors originating from the fact that they don't rely on the 3D information that normally humans intend to use when we try to observe the scene. So these strong 3D clues that can be worked into the framework can help us to overcome errors, for example, accompanied by occlusion or other challenging cases. So our motivation in this work was to create a model that can translate the images as humans do and to understand where the pupils within the scene look in the 3D space. So we aim to fully utilize the 3D information in our framework. Our framework exists of 3 different modules, starting with the relative depth prior module, which input is an RGB image, which goes through an existing molecular depth estimation network. This network produces a priori depth map that we rely on when we are trying to incorporate the 3D clues into our frameworks. Furthermore, we propose the 3D field of view module, which is a novel solution on how we are integrating the people's gaze direction into these given attention target estimation frameworks. A little bit more information on this. The input of this module is the head positional encoding of every given person of the field that we are observing. So we know where their head bounding box is located within the scene. Based on this, we are able to generate the head crops of each individual we are observing. There are existing 3D gaze direction estimation methods that we can apply here to estimate the direction of the person, the gaze direction of the person we are observing, and by this generating individual probability maps. So here is an example that I would like to display. For a given RGB image input, we generated the priori depth map, as I mentioned before, and I displayed the individual probability maps of each individual highlighted and observed within the scene. You can see the ground truth location, the target where these 4 individuals are jointly looking at, highlighted as a white rectangle, and their head bounding box is also displayed on these images. You can see how each individual's 3D field of view differs slightly based on their head direction and where they are looking at. Once we generated these individual field of view maps, we combined them and generated a combined probability map for this scene. What we found is that once we used the given inputs of an RGB image, the generated depth prior map, and this field of view probability map, we used this and concatenated it and used it as an input of the proposed joint attention target estimation module, which was used to actually calculate the target location in 2D of the people we observed in the scene. So here we used ResNet 50-like architecture with an extension of extra convolutional layers and an optional use of non-local blocks inserted, and an encoder in a deconvolutional network to generate the gaze target of the individuals observed in the scene. So here in this example, the ground truth head bounding boxes of the people observed are highlighted as yellow, and the ground truth box target is also yellow, and our estimate is red, which is very, very closely located to the actual ground truth location. To evaluate the performance of our joint attention target estimation model, we not only evaluated it on the joint attention target estimation benchmark datasets, but also evaluated it on single attention target estimation datasets, such as the gaze follow image benchmark dataset, which probably some of you already know, as well as a video attention target dataset, which is a video dataset used for single attention target estimation. Please note that our method does not take advantage of the temporal information. So in this case, we compared with all of these state-of-the-art methods. Some of them may use depth information, and prior already some of them were designed for joint, and some of them were designed for single attention target estimation. Furthermore, we also evaluated our method on an existing joint attention benchmark dataset, the video co-attention dataset, and we found that by formulating the field of view as a 3D probability map instead of a hard-coded cone or just working in 2D, our results improved in all of these benchmark data sets, and we were able to outperform the existing video as well as image-based attention target estimation methods. To better understand all the components of the frameworks proposed, we also performed multiple ablation studies from which one result I'm displaying here. This was performed across all the benchmark data sets previously mentioned, where I show that if we rely on just a particular input, for example, just the RGB image input, or this combined with the depth prior, our method's performance improved every time we add those modules on top of each other. This ablation study basically showed that every single module and element of the proposed framework was very useful in improving the performance, especially the 3D field of view probability map. That was a novel solution of how to formulate a person's field of view. So in conclusion, this work aimed to infer the gaze target of 2 or more people within the STEAM, and this was the first to incorporate the full scope of depth information into a joint attention target framework using the proposed field of view probability map generation module. The results showed in the paper and displayed here as well, showed state-of-the-art performance on both single and joint attention target estimation benchmark data sets. Thank you for your attention.
Yeah, we can take a few questions. Okay. Okay. All right. We have one last presentation before we move on to the closing remarks. Alden, are you there?
Yeah, so
Wonderful. Just a moment, sorry, I'll stop sharing. Okay. Yeah, whenever you're ready, Alden.
all right, are you able to see my screen now?
Sorry, we were, and then I made a mistake. Just one second.
It's okay.
Okay, we're good to go.
All right. So hello, everyone. My name is Haldun Balım. I'm currently pursuing a master's degree in ETH Zurich, and today I'm going to be presenting our work, EFE end-to-end frame-to-gaze estimation. First, I would like to introduce the main problem we are trying to address. As you might know, most of the current gaze estimation solutions use a multi-step data normalization process. And inspired by similar problems in computer vision, we would like to propose an end-to-end solution. We believe that due to the pre-processing steps, the learning capability of the actual model is limited, and the dependency on the external modes induce some systematic errors or biases. So here you can see an illustration of a typical setup. To create a data set, subjects are prompted with visual cues and asked to look at specific points on the screen, and at the same time they are being recorded with the camera. Afterwards, the individual images of the subjects are chosen and matched with point of gaze coordinates. The conventional next step is to use face detectors and facial landmark models to annotate a point called gaze origin, either in the center of the eyes or in the center of the face. And then a vector called gaze vector is found by drawing a line that passes through the gaze origin and the point of gaze. So although point of gaze is deemed as a ground truth, the gaze origin and gaze vector extraction process is not well defined. The gaze origin is merely a virtual point, and the gaze direction is dependent on it. We believe that gaze origin and gaze vector extraction process may cause a systematic bias in the dataset. So therefore, we refer to them as pseudo-labels. So now we introduce 3 different approaches to estimate point of gaze. The first one is to directly regress point of gaze without any intermediate labels. The second one is to train 2 independent models, one for gaze vector and the other for origin, and combine their predictions to yield a point of gaze estimate. And the last approach is to estimate point of gaze using estimated gaze vector and origin, all coming from a single model. The last approach enables model to jointly learn these entities and utilize the information that comes from connecting them. So our main task is to design a tailored approach that belongs in the last class of these models and outperforms the all other approaches. So now I will describe the proposed solution step by step, a breakdown of it. So firstly, we have an encoder that processes the frame input and extracts features which we refer to as bottleneck. And then these bottleneck features will be processed by an MLP to regress gaze vector. The same bottleneck features and some connections coming from encoder will be fed to a decoder, which upsamples the bottleneck and creates two one-channel images. The first one is a gaze origin heat map that attains probabilities to each pixel that represents how likely this pixel on the image is to be the gaze origin's projection. And the other one we call a sparse depth map. Essentially, what it tries to do is to attain a depth coordinate in each pixel. Then using these heat map and depth map, we extract the 3D coordinate of the estimated gaze origin. And the last step is to use camera extrinsics and use this origin and gaze vector to regress a point of gaze. So you can see on the table, we successfully designed a tailored architecture that can outperform the previously mentioned model classes. One thing we want to highlight here is that we have an alternative model called EFE without depth map. And this EFE without depth map approach, we didn't use any heat map or depth map estimation. We just regressed the gaze vector and a gaze origin through a bottleneck with MLPs, which can be seen as the standard multitask approach. And as you can see, this model didn't perform as well as our proposed approach with the depth map. We believe that this indicates rather than a deterministic gaze origin modeling, a probabilistic gaze origin modeling can be more appropriate for this task. And we believe that this also supports the argument that the gaze origin and gaze vector can only be deemed as pseudo labels. So additionally, we tested our model on 3 common gaze estimation datasets, namely EVE, gaze capture, and MPI gaze. And we can see that in all 3 of these datasets, EFE shows comparable performance to state-of-the-art models, although it doesn't use any complicated pre-processing steps. And we also would like to highlight that frame-to-gaze estimation is intrinsically a more challenging problem because in our frame images, the region of interest like face and eyes cover only a limited portion. So lastly, we would like to show one of our ablation studies where we tested our model in cross-camera evaluation setting. So we have in the EVE dataset, we have 4 cameras, and now we train a model for each camera and test it on the other ones. And you can see that the EFE in fact shows better performance compared to what we call FaceNet, which is the conventional approach using a normalization step and the gaze vector regressor. And this also indicates that such estimation process is less biased. So in conclusion, in this work, we showed that joint estimation of gaze origin, direction, and point of gaze can mutually benefit each other. And an end-to-end architecture can show less bias in prediction. And lastly, we showed that similar metrics to state-of-the-art can be achieved without normalization. So you can check out our project page and our paper using the scan QR code. And thanks for listening to us. Are there any questions?
There are actually quite a few questions. We may not be able to take all of them. First. Okay, I think the gentleman in the back.
My question is how the first estimation network is trained. There is no supervision in the network.
Okay, I'll repeat the question to you, Haldun.
It's
Oh,
yeah, go ahead, please.
could you hear?
No, it's not that audible. I would appreciate it.
Okay, how is the sparse depth estimation trained as there are no labels?
Yeah, so there are no labels, and that's in fact correct. So we are not directly supervising the sparse depth map, but using this gaze origin heat map and sparse depth map, we can generate a gaze origin in the 3D space, and then we can define a loss. And since all of these operations are still differentiable, the sparse depth map will be only trained by the actual 3D gaze origins coordinate. But in our paper, you can see some ablation studies. Just by giving a single coordinate, single pixel Z coordinate, we can in fact generate some results that are showing that we have capabilities of learning the depth information, although it's not it's not super reliable to detect all these Z's, but for the gaze origin, it's quite reliable.
Thank you.
I think we have. All right. Okay. We'll take one more question.
Sure.
Yunfeng?
So my question is, so it seems this method is trying to explicitly model like the gaze angle and also the camera kind of angle. But I think that like the 2D gaze kind of estimation, it's actually implicitly to estimate of this one and then output a 2D point, which you also don't need to worry about normalization or all this kind of stuff. So what's the advantage of this method compared to like doing 2D gaze estimation track?
Okay, so
I
we
think
were, oh,
this time I heard well. I think the real, so first of all, we should highlight that in the current well-known gaze estimation benchmarks, the current solutions, the current data sets have really high quality images. So these high quality images, when you're just extracting the face region, is like very efficient to use with models. But in a more realistic scenario where maybe you're in the wild, we believe that these kind of end-to-end approaches may be more appropriate because although we haven't done extensive experiments in the wild cases, we believe that end-to-end approach can have a different attempt at covering these methods. So in our experiments, we couldn't show a significant upgrade on the state of the art, but we believe that this is an attack to the problem from a different angle, and we believe that it can be seen as a promising field of research.
Do I have? Exactly.
Yeah,
I have a
sure,
question.
go ahead.
Exactly the points. Thanks a lot for your presentation. Here benchmark research regarding gaze capture and MP gaze, there is a lot of misannotation. Have you ever checked this quality? So we tried to use this one. We found out many misannotation. So maybe this decrease your evaluation quality. I believe your new method would work well. Therefore, it is very important when you use this kind of data set for reference space, we have to clean up the data. The gaze capture, MP gaze, MP face gaze is contaminated. We could not measure statistically how much. This is not doable currently.
So during our experimentation phase, we widely experimented on EVE. In fact, we did our we just use gaze capture and MPI gaze as it is available on the internet. And I haven't known this issue of the contamination, but for the MPI gaze, maybe Sukong has some more insight. But yeah,
the quality of EVE is quite better than gaze capture, MP face gaze. Something is. From industrial point of view, it is useless, both data. Sorry.
Yeah, no, but thank you very much for your valuable inputs. I think, unfortunately, I would love to talk more, but we would have to wrap up. Thank you, Haldun. Just a quick round of applause for the speaker again. Thank you very much.